propagation of wave, the properties of wave, and so on and so forth about waves. So in this content, I'm going to make sure that I precisely explain wave in a way we can understand and comprehend, and by opportunity, we can derive the wave equations. So today, I want to ask you a very important question before we start this context. Now, what do you see wave as? What do you see wave as? Because when we talk about wave, we are talking about a disturbance, something that causes a disturbance within a medium, and that disturbance transfers energy in form of kinetic energy around different points in that medium without permanently displacing it. Okay? Now, when you hear about a wave, it's a disturbance. Okay? Something that causes a disturbance in the medium is a wave. And when this disturbance occurs, there is a wavefront produces as the wave propagates around the medium. And when this wave begins to propagate, meaning when the wave begins to spread out or travels through the medium, it transfers energy from one certain point to another without permanently displacing the medium. When you're talking about permanent displacement, you're trying to bring in the knowledge of a temporal displacement in the medium. Okay, it doesn't just start from this point and then returns to a new displacement. It starts at this displacement, it propagates, and then it settles, and that's an origin. Okay, now that is what we call a temporal displacement. But when you're talking about a permanent displacement, it's a complete movement of a wave from an initial position to a new position. Okay, now wave does not permanently displace themselves or displace the medium. It temporarily displaces the medium. Now, when you're hearing about wave, what do I say wave is? Wave is a disturbance, okay? It causes energy to be moved or to be transferred from one point to another in the medium without permanently displacing the wave, the medium. So I'm going to write it down now so we can understand it. So we said a wave is a disturbance that transfers energy in form of kinetic from one point to another within the medium such that it doesn't cause a permanent displacement of the medium. Okay? Now, when you hear about wavefront, okay, wavefront, we are talking about that part, that line that contains every vibrating particle in that medium. So as the wave propagates, it travels with a wavefront, with the wavefront, and in that wavefront, there are particles that vibrates as it propagates around the medium. So when you're hearing about wavefront, just imagine as a pattern, a line that contains every vibrating particle in that medium. Okay. Now, wave, we have two classifications of wave, and because of this classification, we began to see that we have mechanical waves and electromagnetic waves. But today we're going to fully concentrate on mechanical waves. Now, what are mechanical waves? Mechanical waves are waves that requires a material medium for their propagation. And when you hear about propagation, you're just having in mind that we're talking about the travel of the wave, how the wave spreads out within the medium, how the wave spreads out in the vacuum, so to say. So mechanical waves are those type of waves that requires a material medium for their propagation. When you talk about a material medium, I want you to have it in mind that we're talking about a means by which the wave travels through. Okay, okay. that substance or that material or that space that the wave travels through. That's what we refer to as a material medium. And why do we say that mechanical waves require a material medium? Without the material medium, the mechanical waves cannot be propagated. Now, when you're talking about mechanical waves, we have examples of mechanical waves. We have sound wave. Sound wave is a mechanical wave because its medium is what? Air. Air is the medium for sound wave to propagate through. Okay, and when sound wave begins to propagate, okay, like as I'm speaking to you right now, I am causing a disturbance in the particles in the air, and when the particles gets agitated, it begins to vibrate and move further away. Okay, and as the sound wave is being propagated, it's longitudinal. It's not transversal. It's longitudinal. Okay. Now, another example of mechanical wave is water waves. Okay, you notice that when you throw a stone into a fluid, it causes a circular waveform to flow or to propagate around the medium. I get it. So the medium for the water waves is the water itself. Okay. Now that water is that medium for the propagation of the water waves, for the ripples to propagate around uniformly in the medium. I get it. And now, why electromagnetic waves are waves that requires no material medium for their propagation? When you talk about electromagnetic wave, it's a variance between two different fields, electric field and magnetic field. So when this variance occurs, it creates what we call electromagnetic wave radiation. I get it. So electromagnetic waves are waves that requires no material medium for their propagation, and most of this electromagnetic wave travels at the speed of light. Example of electromagnetic wave is the visible light we're seeing, is the ultraviolet rays, is the violet rays, is the X-ray, the infrared red, and so on and so forth, the gamma rays and beta rays. Now, there's so many electromagnetic waves, but at this content we are literally dealing with mechanical waves. Right? We're dealing with mechanical waves. And we say that they are waves that requires a material medium for their propagation. So when you hear about mechanical wave, we are dealing with a material medium that requires the wave to travel through or to propagate through it. Okay? Now, we have types of wave. Very, very much interesting. We have types of wave. We have transverse wave and longitudinal waves. Okay? All these waves are very, very important. These are the two main types of wave we have. We have transverse wave and we have longitudinal waves. Okay? Now, transverse wave are those waves that travels perpendicularly to the vibration of the medium. Okay? Let me give an illustration. This is my stone, and this place is the water. Now, when I throw this stone into the water, you will notice that the stone sinks. And if I place a floating material on the surface of the water, as the stone sinks into the water, you will notice that floating material moving up and down, and the wave propagates towards this direction. And as this material is oscillating up and down, it's still flowing in line with the vibration direction of the medium. Okay? Now, this is a vertical oscillation, and this is a horizontal travel. This is a horizontal travel done by the wave propagation, and this is the vibration of the particle vertically to the direction of the waveform, of the wave. Okay? Now, if you understand this concept, you will know that the vibration of the particle is vertically oscillating, and the direction of the wave is horizontal. Right? Now, the intersection of a vertical line and a horizontal line creates a perpendicular angle. Okay? Now, we refer transverse waves to as waves that are perpendicular to the vibration of the medium. Now, with my illustration, we can further say that this is the vibration of the medium. No, this is the vibration of the particle, and this is the direction of the wave travel. Right? And now, every wave is a sine graph. Every wave is a sine graph, meaning that every wave starts from an origin. Right? Now, this is a diagram of the longitudinal waves. Okay? These are waves that are perpendicular to the vibration of the medium, to the vibration of the direction of the wave travel. Now, these are what we call transverse waves. Okay? And while longitudinal waves are waves that travels parallel to the vibration of the medium. An example of longitudinal waves is the sound wave we all know. Example of the transverse wave is water waves. We talk about water waves, light waves, and so many others. The wave generated in a rope. Okay, all those are transversal waves. Electromagnetic waves are transversal waves because they travel perpendicularly to the vibration of the medium, while longitudinal waves are waves that travels parallel to the vibration of the medium. In longitudinal wave, we have something we call the compression region and the refraction region. Now, the compression region is that region such that the pressure in the air is much, so the clutter, okay? And while the refraction region is that widens and the pressure in the air is less. Let me show you a proper diagram of a longitudinal wave. As a longitudinal wave is a sound wave, this is how it propagates in air. Now, this compressed part is called the compression region, and this space part is called the refraction region. The compressor region, the refraction region, and the compression region. So this is a longitudinal wave. This is a transverse wave, and this is a longitudinal wave. I get it. So we have two classifications of wave: mechanical wave and electromagnetic wave. And on the mechanical wave, we have types of waves. We have transverse wave and longitudinal waves. And transverse wave are waves that travels perpendicularly to the vibration of the medium, while longitudinal waves are waves that travels parallel to the vibration of the medium. Now, I want to formally introduce terms used in waves. In wave motion, there are certain terms used to describe a progressive wave. When you talk about a progressive wave, you're talking about a wave that continues to transfer energy as it propagates away, further away from the source of disturbance. Okay, that is a progressive wave. Now we have something we call the amplitude of the wave. That is one of the terminology used in expressing wave propagation. Now, the amplitude of the wave is referred to as the maximum displacement of the wave, right? It is that maximum displacement of the wave. So the amplitude is referred to as the what? The maximum displacement of the wave. The particles attain a maximum height, and at that height there is no further height higher than that height. So that is what we call the maximum displacement of the progressive wave. Alright? And now I'm going to use a realistic diagram to explain what I'm trying to say. So first of all, we talked about amplitude, meaning is the maximum displacement of the wave. Okay? Or the maximum displacement of the vibrating particle in the wave propagation. All right, and now we have something we call the crest. The crest of the wave is the maximum oscillation upward, okay, of the vibrating particle. And we have something called trough. The trough. The trough is referred to as the maximum displacement of the vibrating particle downwards. Okay. All right. Now, since we've known that, I want us to understand what we call the wavelength of the wave. All right. This is very, very essential. Literally essential. Now, the wavelength of a wave is referred to as the maximum oscillation of a vibrating particle between a successive crest and a successive trough. Alright? So the successive maximum oscillation of between the crest and the trough is referred to as what? Wavelength. Wavelength can also be defined as the successive oscillation between two crests or between two troughs. Alright? Now, we're also talking about frequency. Frequency is the number of oscillation done through per time taken. Okay? The number of oscillation per time taken. The number of oscillation done through by the vibrating particle. The number of oscillation covered by the vibrating particle per time taken is what we call the frequency. Now, the period of the wave is the number of time taken to complete one oscillation, to complete one cycle. Alright? Okay? Understood? Now, I'm going to draw a diagram of a progressive wave for us to really understand this very well. And after that, this is what a transverse wave diagram. And every wave starts from the origin as it propagates through. Alright? Now, here is called the y-axis, and here is called the x and the time axis. Alright? And now, this is the maximum displacement of the vibrating particle, which is the A. So everything here are maximum. And all these are called the what? Amplitude of the wave. Alright? And now the successive oscillation between two crests is what we call the what? Wavelength. Alright? So between this and this is the wavelength. Understood? Now, when we also talk about the x component, the x component is the horizontal displacement of the wave ranging from the origin to other part as the wave progresses through. Okay? Now, from here to here is the horizontal displacement of the wave, and from here to here is the vertical maximum displacement of the wave. Right? And this is what we call the trough. Right? And this is what we call the what? The crest. Or this here are the crest. So this is a diagram illustrating a progressive wave. Now, we are going to start deriving equations, okay? And we're trying to show the relationship between the speed of the wave, the frequency of the wave, and the amplitude of the wave, okay? No, the frequency of the wave, the wavelength of the wave, and the speed of the wave. So we're going to derive an equation that shows the relationship between these three identities. Okay, starting from the definition of velocity, we know that velocity is what? Distance, right? Over time, right? And the distance covered successfully is what we call the wavelength, right? Over time. And this time is in capital letter. So V equals to what? Over time. Any confusion? So we are going to furtherly continue. And now, since this equals to this is what we call equation 1. Equation 2 is making the lambda, which is the wavelength, the subject of the formula of equation 1. So making it the subject formula, you cross multiply, and it's giving you V, the T, and this is your equation 2. Alright? I get it what I'm saying. Now, remember that frequency frequency f equals to 1 over t, right? So now, in equation 1, we know that v equals to over t, right? So we can further express this equation as v equals to 1 dot t and 1 over t dot wavelength. Now, when all these things equal to frequency, we say put f equals to 1 over t in the system. So, having that we have that v equals to what? And this is the equation 3. This is a very, very important equation in wave, ranging from this to this and down to this. This is very, very important.